Woohoo, and welcome to 13.2, the definite integral. This particular section is one where you're really going to get shortchanged by the fact that this is a class that's supposed to cover so much and only include an introduction to calculus. If this were a full calculus course, we would devote at least an entire week to this idea, and we would have devoted a couple weeks to its introduction. So we would have developed this. And instead, you've got a couple of sections. We say, isn't this nice? And mostly we tell you how to use it. So for the most part, 13.2 is going to be all about how to calculate these values. But I did want to give you some understanding, some foundation for what the heck is going on, because something really, really big is happening. Now, when I first wrote this up, I wrote this beautiful paragraph, which you can read through here or in the notes, leading up to this concept called the Fundamental Theorem of Calculus. And mathematicians don't take things lightly. When we call something the fundamental theorem, we mean it is fundamental. This is the big one. This is the theorem. This is the idea in calculus upon which everything else is built. However, when I read over this, I realized that this whole paragraph probably sounds like blah, 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 blah. So instead of doing blah, 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 I want to talk about this. I found, and you can see I've covered this up, so you don't worry about the unimportant things yet. We'll get to that. I found this image in Wikipedia. Yay, Wikipedia. And I wanted to talk to you about the definite integral. So this is a definite integral. And I can't spell what I'm talking. There we go. A definite integral, you'll notice, is different from an indefinite integral in that I've got a and b floating around, and we didn't have those before. And literally, that's it. It's defined. It's defined over an interval. What the heck does this mean? Well, we're taking the concept of an integral and we're looking at it in a particular spot. And you'll see here's a, there's a, that's the beginning of our interval. Here's b, there's b. And the area under the curve is what the definite integral was defined to be. And so it's interesting here because when I say area under the curve, I mean between, so this is f, lowercase f of x, between this curve and the x-axis. And the thing to keep in mind is we do something really interesting as mathematicians, and this has a lot of different reasons. And if you want to talk to me about it, let's talk. I would love to talk at length about integration, about calculus. It's really cool. It's just not all included in this particular class. But basically, this little green piece right here has an area. This other little green piece, a lot bigger green piece, also has an area. Both of these areas are considered positive because they occur on the above the x-axis. This area, now technically areas can't be negative, but we subtract this area because it falls below, because these values are negative. So we've got not a negative area, but if we were going to add them up, like if I knew this was 1 and this was 2, I would say 1 plus 2 is 3. And if this were 5, I would say 1 plus 2 is 3, minus 5 is negative 2. So the total area here, and again, it's a weird concept, is negative 2, which would tell me that more of it sits under the x-axis than sits above, right? Positives were above, negatives are below. And that's what a definite integral is. Now, I've got a bunch of papers here because then we say, okay, let's imagine now another function. And this function is going to be related to f. I always think of it as like a parent of f. It is the antiderivative of f. So if you take the derivative of capital F, you get lowercase f. So I have a big function. That function is not graphed. This is the derivative function. This is the derivative of capital F. This is this. This is the derivative function. And We have something in math called the Fundamental Theorem of Calculus, and that tells us, dun 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 dun, this is the very exciting thing. And if you were around, if you were alive when everyone was hashing this out, this was major. This was this big, amazing thing. The Fundamental Theorem of Calculus tells us that the area under the curve, the sum of the green, the pluses and the minuses, is equal to the definite integral between a and b. So basically what that's saying is just add up all this area. These two are equal. But that is equal to, and this is kind of weird, you take the parent function, the antiderivative function, the capital F function, and all you have to do is evaluate that at b, right there, the end of the interval, and subtract capital F again at a. And this was like, blew everyone's minds. This was amazing. And it was so important, so foundational, that it is called the Fundamental Theorem of Calculus. And you can see that I wrote it there. There's a lot of details. Again, this is really big, deep stuff here. However, what are we going to do with it? Well, we're going to use it to discover things about business and economics. So, for example, if I get a problem that says evaluate the integral, the definite integral between 2 and 5. How do I know it's definite? There are numbers there. Between 2 and 5, a 4x minus 6 dx. You remember the dx from the indefinite integrals. Okay, then what should I do? Well, what it's asking us to do is it says you have to first anti-differentiate or take the integral. So in other words, what we're going to do is we're going to take the 4x minus 6, remember the 4x, if we anti-differentiate, becomes 4x squared over 2, right? The minus 6 becomes minus 6x. And then I personally, everyone has a slightly different way. I was taught to draw this little half a bracket and then write 2 and 5. So we've moved the 2 and the 5 to the other side. At this point, you're like, what the heck is going on? And the answer is, it is what it is. So as far as this text is concerned, all you need to be able to do is take the antiderivative, so go backwards with differentiation, and then go ahead and apply the two numbers. So I'll show you what that looks like. First, I'm going to simplify this. 4x squared over 2 is 2x squared minus 6x. Okay, so this is the antiderivative, right? This is the antiderivative of the 4x minus 6. Okay, so far so good. And I'm going to evaluate it between 2 and 5. That's this f of b minus f of a. So the really, really amazing thing is, even though we've got this whole area and this whole thing, what it's saying is, well, that's with lowercase f. But if you know what the antiderivative is, you only have to evaluate it at 2 spots. So I'm going to apply 5. There's the 5, right? So if I call this one the pink one, the upper limit, here's that. And then I subtract the lower limit, 2 times 2 squared minus 6 times 2. And I'll call that, well, we already used green, so let me use blue for that. Okay, so far so good. Is this all making sense? Okay. So then I get 2 times 25, so that's 50 minus 30 minus 2 times 4 is 8 minus 12. So that's 20 minus a negative 4, which is 20 plus 4, and I'm over to the, off the side, equals 24. And that's the other thing to know about calculus. Calculus always takes more space than you think. Okay, so hopefully right now you're like, okay, this is weird. And also, hopefully you're also asking a question, where did the C go? Where did the C go? Let's look. I said, here's the antiderivative, but there's no plus C. Let's take a look at that. Okay, let's say our antiderivative is, let me copy it down, 2x squared minus 6x plus c, right? We learned that from the last chapter. Okay, so let's evaluate that at both 5 and 2. Okay, so let's say at 5, we get 2 times 5 squared minus 6 times 5 plus c. So that's going to be 2 times 25, which is 50, minus 30 plus c, which equals 20 plus c. So far, so good. Then at 2 times 2 squared minus 6 times 2 plus c. Okay, so that's 2 times 4, that's 8 minus 12 plus c. So that's negative 4 plus c. Okay, so I evaluated at 5, I evaluated at 2. That's the fundamental theorem of calculus. Do it at each endpoint, evaluate the antiderivative at each endpoint, and then subtract them, right? So I got to subtract it right there. So capital F of 5 minus capital F of 2 equals 20 plus c minus negative 4 plus c. Okay, so that's 20 plus c plus 4 minus c equals, and then what happens to the c's? The plus c and the minus c. They disappear. And our answer is 24. So what's happening to the c? Well, when we did this f of b minus capital F of b minus capital F of a, since each one has a c in it and we're subtracting them, the c's will always cancel out. So when we're actually working with a definite integral, we choose the antiderivative that has a plus 0. Right? We talked about the fact that plus c could be many different things. It just depends on the specific version. We don't have to worry about it. It's going to cancel out, so we choose the one that equals 0 because it's just easier that way. Okay? Kinda, sorta. I know everyone's like, what is even happening here? And the answer is, that is a really good question. And I encourage you, come talk to me, talk to the tutors, watch videos. It's all, calculus is pretty amazing. Okay, so let's look at this. You'll notice this looks very similar to the first problem. And this one is evaluate the definite integral between negative 2 and 5 of 4x minus 6 dx. And again, the dx just, it has to be there. Remember we talked about that with the definite integral, or the indefinite integral. So first thing you do is you have to integrate or anti-differentiate, but I've already done that. I'll go ahead and do it again, right? X goes up to x squared and I divide by 2. Just a constant goes up to 6x. I go from negative 2 and 5. And remember, we can skip the c. If you really want to, you can put the c in. When I was first learning calculus, I always included the c. So if you want to put in a plus c there, that's fine. It works out. So it's up to you. So I'm going to evaluate with 5. So 4 times 5 squared over 2 minus 6 times 5. I didn't even simplify this time. I'm so excited about getting to the answer. And then I'm going to evaluate with negative 2. 4 times negative 2 all over 2 minus 6 times negative 2. Okay. So let's see. 5 was the same upper limit. the 5, oh, sorry, yeah, there. The 5 is the same upper limit, and I didn't write that in, so let me write that right here, upper limit. And then this is the lower limit. Is this the same problem? And the answer is it's very close. The difference is the lower limit here is -2, not +2. Okay, so let's calculate. 4 times 25 over 2 is 100 over 2. It's 50 minus 30 minus, okay. Oh, I left something out. Do you see what I'm missing? I left out the squared. Sorry about that. So over here, I've got 4 times the quantity -2 squared. -2 squared is 4. So it's 4 times 4 all over 2. Minus 6 times -2 is plus 12. So let's see, this is going to be 20 minus 8 plus 12. So it's 20 minus 20. So the whole thing is going to give me 0, which is kind of interesting, isn't it? Kind of woohoo, little bit woohoo. What do you guys think? Okay, so woohoo. I'm going to stop there, let everyone kind of let this soak in, because that was a lot. I'll continue on in the next video with this one. Remember that at this point now we've got, and it happened very quickly for us because we just kind of said, ta-da, and then we had it. So we didn't really work for it, but we now have a connection between integration in terms of the indefinite integral and integration in terms of the definite integral. And the definite integral, which is the area under the curve, is equal to f of b minus f of a, where these f's are the capital F, and they are the antiderivative of f. Okay, it's a lot. Congratulations for getting this far. Woohoo, you're awesome. Math on.